Right, so we do have our first problem now in our FE prep. So our problem says you have a capacitor with 400 microcoulombs of charge right here, and these are the dimensions for a parallel plate capacitor. So a parallel plate capacitor, if you look at it, has two plates separated by a dielectric medium, and this distance between the plates is known as distance d. And if you look at it from the front, the parallel plate capacitor is going to have an area A. All right. So our objective here is to find the voltage. So we already know that this capacitor has been charged previously and it has 400 microcoulombs of charge. And we want to find out, okay, now we have removed the voltage supply. Now what is the potential difference this capacitor is if we hook up a voltmeter to it? What is it going to read? So let me explain it a little better. So we have our parallel plate capacitor. We have hooked it up to a voltage source and got up to a point where now this has 400 microcoulombs of charge. Now I'm gonna remove this voltage source and measure the voltage right here. So that's the question. What is this voltmeter gonna read? So let's get to solving this. So the first thing, if you look at our expression, was we're going to use our first expression. The charge is capacitance times voltage. Now if you just rearrange this, voltage is the charge divided by capacitance. And so for that, we have a missing term in our problem. So I'm going to write the main formula right here. Right, so Q is equal to C times V. So V is Q by C. So we have a missing term, that's C. So let's go ahead and find C first. So the formula for capacitance of a parallel plate capacitor is given by epsilon times A by D. So this A is the area of the parallel plates and D is the distance between them, and epsilon is known as permittivity. So it's just a measure of how much of your electric field lines can pass through that dielectric medium. So if you look at the very first diagram, I showed you so if you have charges here, there's going to be electric field lines shown in the yellow. So it's just a measure of how many field lines that can pass through that dielectric medium. So that is the permittivity of the dielectric medium. So in this case, the problem has not said whether it's air or glass. So we can safely assume it's air. And for air, the permittivity is 8.85 into 10 power minus 12 farads per meter. Now, if you're using something like glass, right? So what you would do is to get the epsilon value, let's say, you would multiply epsilon of air times epsilon r of glass. So this epsilon r is known as relative permittivity. So with respect to air, how is the value? All right. So now we know what is our epsilon, and we know our what's A given in the problem, 0.02 meters square, and we know our D. So we can easily find C 5 into 10 power minus 12 times 0.02 divided by 0.01. Very simple calculation is gonna give us 1.77 into 10 power minus 11 farad. So this can be also like 17.7 picofarad. So it's minus 11 right here. Okay, so now in this was our main formula, and we had capacitance value missing. So now we know how to find the value of capacitance of a parallel plate capacitor. All right. Now let's go ahead and solve the rest of it. So we had our as 1.77 into 10 power minus 11 farads per meter. So our voltage or potential difference is nothing but charge divided by C. So the charge is 400 microcoulombs divided by C is 1.77 into 10 power minus meter. And this is going to give you 0.6 into... Whoa! So just take a look at this. That is a very high voltage value. So the problem is we had 400 microcoulombs of charge, and if we find the capacitance and then find the potential difference across it, it is massive. So very important lesson: do not touch a capacitor with your hands. So what do? So if you see a capacitor lying around, so it's probably gonna look something like this. So you would first want to hook up a voltmeter and read what is the voltage across it. So if it's a dangerous voltage, all you gotta do is remove the voltmeter and connect a resistor across it. So if you connect a resistor, the current is gonna flow through it, and the heat is gonna get dissipated, energy is gonna get dissipated, and you're pretty much safe. And you gotta measure the voltage again. But please, do not touch a capacitor. It can be very dangerous. All right, let's go to our next problem. So our next problem says the capacitance value is 200 microfarad, and we are connecting it to a time-dependent voltage source. So find the energy of the capacitor. So we will make use of our second formula. E is equal to 1 by 2 CV squared. I think we pretty much have everything needed to solve this problem. So let me go ahead and write it down again. E is half times CV squared, or in this case, time-dependent voltage. Yes, it looks like I have pretty much everything. So that's going to be just half times my capacitance is 200 microfarad times 240 sine 377t. So this is of the form, V of t is equal to V sine omega t plus phi. The phase shift is 0 in this case, so this is 0. T is as it is, and omega is 377 radians per second. And your V is 240 volts. All right, so this is a time-dependent source. So nothing complex out here. So all we got to do is use the formula for energy, and this energy exists because the capacitor contains some charge. All right, and it gets charged and discharged depending on the time. So our energy is also probably going to be dependent on time. So if we just solve this entire thing, we would get 5.76 sine square 377t.